from this contradiction at the level of the classical to quantum transition. So this is a very general overview of this talk. I will introduce a bit the framework of objectivity and the classical to quantum transition. Then I will discuss as first example ideal projecting measurement and the thermodynamics of ideal projecting measurements. And using the tools that I will introduce here, I will shift to intersubjectivity of outcomes and the thermodynamics of this other framework. I will show you that ideal intersubjectivity is not perfectly attainable, so I will define a weaker notion, which is what I call bias joint information broadcast, and I will try to understand how close we can get to ideal intersubjectivity and using different approach. And one of these is coarse grain. I will focus on that in the fifth part of this talk, and also I will compare to a standard model of objectification. And then I will give you some conclusion and future perspectives of this work. So let's start from the introduction. So everything started basically from the classical to quantum transition framework started basically from quantum decoherence, which is the understanding of the fact that coherent superposition due to interaction with larger environment basically transformed to classical mixtures. A further step in the understanding of the classical to quantum transition came from understanding that the environment is not like something that we have to trace out, but is actually what we use to access a system. So the environment is basically promoted to have an active role in the process of the classical to quantum transition. And quantum Darwinism is based on this observation, that we always access the system by accessing some fraction of the environment that interact with the system. And one way to say that we can really access the information about the system from accessing the fraction is to say that the quantum mutual information between a system and a small fraction is approximately equal to the von Neumann entropy of the system. So that accessing a fraction is basically the same as accessing the system. The information about some observable of the system is encoded in the fraction of the environment. And to have a proper classical to quantum transition, the fraction of the environment cannot be too large. So here I plotted two different quantum mutual information for two different examples. The red one shows this what is called the classical plateau. We see that we need very small fraction of the environment to access basically all the information about the system. And this adding more fractions does not really increase our knowledge about the system. On the other hand, the green one instead needs almost half of the fraction to access the information about the system. So it does not really represent a process that describes a measurement or a classical to quantum transition in this context. A further refinement of this concept was given in the last decade from Korbitz and co-authors, which noticed that this was also known by Zurek, but in the quantum Darwinism, there are some quantum correlation hidden. There are some hidden quantum correlations. So they realized that they needed a sort of more operational way to define objectivity and the classical to quantum transition. So they give this definition, a state of the system X as exists objectively if many observers can find out the state of the system independently and without perturbing it. And from this definition, they formalized all the aspects in this definition. They found a specific structure of states that satisfied this definition. And then they are known as spectrum broadcast structure, and which is given in this form is basically a classical states where there is a convex mixture of the projector I, so the projector I, so corresponding to the outcome I on the system, tensor some other states on the environment. This is a multipartite state, the rho I, and with the following property. So each rho I is orthogonal to each other, so they can be perfectly distinguished, and there exists a measurement that do not disturb these states. So measuring this observable will not disturb the state. And so we have no discord within this structure. So this is a subset of quantum Darwinism, because in quantum Darwinism, we might also have some disturbance, which is excluded from the definition in this more refined definition. Yeah. So a further step, which is not really a refinement, but is a slightly different approach, was given from Ozawa in the last few years, which defines something that is slightly different, and I will use today, which is what I and Ozawa call intersubjectivity. The first difference is that we are not speaking about a property of a state, but more a property of a dynamics of a process. So intersubjectivity is defined as the process, a property of a process such that many observers, so we still have many observers in the picture, can access information on the initial state of S. So we see that we make a distinction between the initial time and the final time of the interaction. And again, they all agree on the outcome they observe. So we do not really ask the coherence or no discord in this picture, but we just ask that we can access some information on the initial state of S and some agreement property. So it's really a definition on the broadcasting of information and agreement between parties. So just to visualize a bit the relationship between these three different definition and different properties. Here I have some sort of map in which quantum decoherence includes both quantum Darwinism and quantum objectivity, and quantum objectivity is a stricter subset of quantum Darwinism. And so where intersubjectivity falls in this picture, well, it's a bit like a sort of intersection. So, of course, quantum Darwinism satisfies intersubjectivity, but, sorry, intersubjectivity includes quantum objectivity, so all SBS states satisfy the property of intersubjectivity, but not all states that satisfy intersubjectivity are SBS states. So there might be some disturbance in that case, so we can fall into also the quantum Darwinism set. On the other hand, we do not ask decoherence on the system side. So there is also a part of the process that satisfy intersubjectivity that might not satisfy quantum decoherence. So the question is why I'm looking into this specific definition instead of quantum objectivity or quantum Darwinism. Because for some reasons, first, of course, most of the relevant cases falls into this set, so we are safe from this perspective. And second, because we can use some tools that comes from the topic of ideal projective measurement, which I will include in the next few slides. And these tools allow us to ask how close we can get to ideal intersubjectivity with thermodynamics resources. So within this framework, we can ask the cost of establishing a certain type of correlations, and so we can establish the cost of approach the ideal intersubjectivity. So we can ask how close we can get to this definition. So for this reason, I will quickly review ideal projective measurement with finite resources, such that we have an idea of how these finite resource frameworks apply to ideal projective measurement, and I will extend this to the definition of intersubjectivity later. So let's start from ideal projective measurement and thermodynamics. So ideal projective measurement can basically be described as the interaction between a system and a pointer environment. We can call it in different ways, but it's always the same. It's a bipartite system, and we want to measure a certain observable on the system by measuring some observable on the environment. And I will decompose the environment into subspace, which would support on the pi x, in a way that the initial state is diagonal with respect to this, the basis defined by this pi x, And I can write the state of the system, initial state of the environment, sorry, as the sum over this AX, this sub-matrices. Here I plot it for dimension 3, but this is general for let's say, for the S is the number of outcomes, so it's not specifically dimension 3. Of course, each of these AX can be larger, so it might not be just a rank 1 projector, but it can be larger if we are measuring a system with a larger environment, which usually is the case. For instance, if the state of the environment is a thermal state, we can write each of the AX as the sum over the energy against state times the thermal, the Boltzmann factor. So now we can ask what's an ideal projective measurement. So we identify 3 properties that characterize ideal projective measurement. The first one is what is called as faithfulness, and it's basically a property that can be written in this way. So the fact that there is a perfect correlation between the outcome X and on the system and the measurement operator on the environment. So if this property is satisfied, there is a perfect correlation between the outcome X and on the system and the outcome X on the environment. The second property is unbiasedness. So this property says that the probability of measuring the post-interaction state is the same as the original probability of the observable we want to measure. So we are basically correctly reproducing the probability that we want to measure. So we have no bias in this measurement scheme. And the third property is non-invasiveness. Non-invasiveness says that the diagonal elements on the post-interaction state are not changed during the interaction. So we have not disturbed, not the whole system state, but at least the diagonal elements that we want to measure. So we can ask if these 3 properties are somehow connected, if there is a relationship, if there is some implication between the properties. And the answer is no, because we can find for each of them an example that does not satisfy the other 2 properties. So for instance, let's take the swap. This is an unbiased, this satisfies property of unbiasedness, but not faithfulness and non-invasiveness. But what's important here is that any 2 properties, so if 2 properties are satisfied, then automatically the third is satisfied. So if the unitary interaction satisfy unbiasedness and non-invasiveness, then faithfulness must also be satisfied. And this is the same for all the 3 possible pairs. And at this point, we can ask if there is any incompatibility with the law of thermodynamics. And as I said at the beginning of my talk, I will take as law of thermodynamics, in this case, just the third law. So the fact that no quantum system can be cooled to the ground state in finite time and with finite resources, such as energy and complexity. So basically, it's impossible, to prepare a state that is not full rank. So our initial resource will be forced to be a full rank state, and we can always think this as a state of a thermal state with specific temperature. So third law basically says that we are forced to take this full rank state. But assuming unitary evolution, the state of the rank of the full system and environment is preserved. And given that faithfulness, which is a property of that we discussed before, establish perfect correlation between system and environment, if this property is satisfied, then the final state, rho tilde SE, cannot be full rank, because this property basically says that all the state is just on supported on a subspace of the whole Hilbert space. So we see that initial full rank and the unitary assumption basically is incompatible with the fact that the rank must be deficient after the interaction. So we must conclude that assuming an initial full rank state, we cannot exactly satisfy faithfulness. So this is the first limitation at the level of ideal projective measurements, the fact that the faithfulness cannot not be perfectly satisfied if we have a initial full rank state. This causes a sort of domino effect, because we can ask if ideal projective measurement cannot be exactly satisfied, what do they look like? And as I said before, non-invasive and unbiased implies faithfulness. But as a consequence, unfaithfulness implies that, so the logical negation of this statement is that if faithfulness fails, then we have either a biased or an invasive measurement. So not only the measurement scheme cannot be faithful, but also it must be either biased or invasive, depending on the measurement scheme we are considering. So just assuming the third law of thermodynamics, we have this sort of no-go theorem that says that an ideal projective measurement can only be just or unbiased or non-invasive. And one can also ask what's the maximal correlation that one can achieve. So what's the closest can be achieved to the closest we can get to faithfulness, and this can be done, was studied by Elena Gurenova and co-authors, and this quantity depends on initial temperature of the environment. Okay, so this basically put the foundation for also our study on intersubjectivity. But first, I need to introduce what's intersubjectivity. So, as I defined before, a process yields to intersubjectivity if many observers can access information on the initial state of S, and they all agree. So, formally, we can split these. Okay, so we have an interaction between a system and multiple environments, and we can split this definition in three parts. First is that many observers, so we have a sort of locality notion. I'm defining here the intersubjectivity just for two observers, but it's basically the same for multiple observers. It's just it's more compact. So we have basically two local measurements and a joint probability on the post interaction state. Okay. The second one is access information on the initial state of S. This basically is something similar to the probability reproducibility condition that I showed you before. So if the probability of observing a certain outcome X on the initial state of the system is PS of X, and the probability of observing a certain outcome X measuring the environment, EJ, then the fact that they access the same information means that the probability that the outcome X is observed are the same between the two environments, and they are the same as with respect to the original probability on the state of the system. And as the last step, they all agree on the outcome they observe. This property can be stated as the agreement property, so that the probability of observing two different outcomes between two different fractions of the environment is zero. Or alternatively, it's the fact that the final state of the environments is supported only on the agreement subspace. So, okay, we have these three properties that they formally capture this intersubjectivity framework. And there is a theorem from Ozawa that says that similarly to the property that we observed in the ideal projective measurement scenario, if two measurements satisfy locality and probability reproducibility, then the pair of measurement also must agree. So again, locality and probability reproducibility implies the agreement condition. So again, we can ask if there is any constraint that the thermodynamics put to this property, to this ideal property of intersubjectivity. And the answer is yes, because the argument at this level is basically the same as the the argument in the ideal projective measurement scenario. So again, we have a full rank state as our initial state of the environment, and the unitary evolution preserves the rank. So a rank deficient, we cannot reproduce a rank deficient state even at the level just of the environment. So again, initial full rank state, so third law of thermodynamics, is incompatible with this rank deficient state property that is agreement. So the third law of thermodynamics implies basically that we cannot satisfy agreement exactly. But since agreement is as a consequence of locality and probability reproducibility, again we see that either we have to renounce either to locality or probability reproducibility. And given that locality cannot really be, we think as locality as more fundamental at the level of definition of intersubjectivity, what we have to give up is really probability reproducibility. So just assuming the third law of thermodynamics is basically, we do not have ideal intersubjectivity anymore. So no agreement, no probability reproducibility exactly. But as I said at the beginning, I also want to study how close we can get to this. So I had to define a slightly weaker notion of ideal intersubjectivity, which I call biased joint information broadcasting. Here we still have a probability distribution that is broadcasted, but it's not exactly the probability distribution on the initial state of S, because we cannot do that given the theorem that I showed you just the slide before. And so I define something that is still, the probability on the environments are the same, but they do not reproduce exactly the probability of the initial measurement on the system. And so the question is how close we can get to ideal intersubjectivity, and to do so, I will study what I call optimal biased joint information broadcasting. So to quantify the deviation to ideal intersubjectivity, I basically define these two functions. One is bias, that measure the deviation of the probability on the environments from the original probability, and the ideal value goes to 0 in the ideal case. And the second one is the agreement property, which measures how much the final state on the environment is supported on the agreement subspace. So how much the different environments will agree on the outcome they observe. And the ideal value is 1 in this case. And we proved that this agreement specifically is, okay, so what's the maximum agreement that we can get and the minimum bias? And the question, we answered this question by showing this upper bound on the agreement. So if we have our initial state that is defined in terms of these different sub-matrices, and each of these sub-matrices has some trace, we call this AX the trace of these sub-matrices, we can show that the agreement is upper bounded by this function, which is the sum over the power of n, when n is the number of environments that need to agree. And we call this upper bound gamma. And we can show that there is a unitary that saturates this bound. So this is a bound only for the unitary transformation that satisfies the biased joint information broadcast that I defined before. And we can also show that there is, for this optimal unitary, an expression for the bias. It's not really relevant to go into the definition of these probabilities, but to see that the bias is basically proportional to 1 minus gamma. So as soon as we approximate a maximum agreement, we also get a perfect bias. So, okay, a very, very quick sketch of the proof. The idea is basically that we can split the interspace of the environment into agreement subspace and disagreement subspace. And we can perform an unbiased information broadcast only on the agreement subspace. And this fixes the unitary on this part of the Hilbert space. And by using the property of biased joint information broadcast, we can basically fix the evolution on the overall Hilbert space. So we use the result from the ideal projective measurement to fix the unitary on a subspace of the Hilbert space, and the property of information broadcast to fix the other part. So just to give you a very quick sketch of the proof. At this point, we can ask, okay, the key quantity seems to be this gamma function, and how it behaves. First, we need to see how we can maximize this function, because we want to have this function as close to 1 to have the maximum agreement. So the first step in this regard is to concentrate the largest eigenvalues in the A0 submatrices, and the second largest eigenvalue in the submatrices A1, and so on. In this way, we basically maximize this gamma function. And once this order is set, we have three different ways to further increase this gamma. The first one is, of course, cooling the environments, which means that we increase the beta and also the A0 increase, while all the other X will decrease. So, of course, this is obvious that by cooling the environment, we will get closer to ideal intersubjectivity. A second step is by coarse-graining the environments. I will discuss this in more detail in a few slides. But basically, if we group environments into macro fraction, we can, in a way, also redefine each of the submatrices, and we can show that this also will increase our gamma function. Or we can have larger environments, so more energy levels will contribute to have larger gamma. Okay, so as I said, coarse-graining. We can, by coarse-graining here, I mean like incorporating subsystem into larger macro fraction, and we can formalize this by considering like a certain set of environments of size LCG. Well, LCG is the size of the coarse-graining, and this is given, of course, by this matrices. I can redefine the AX for this coarse-grain in a way that each of these will be now depending on the size of the coarse-grain. And so the corresponding gamma function for this coarse-grain is given by this mu and x. And we can show that we can concentrate larger values in the A0 in a way that this gamma function scales with the size of the macro fraction in an exponential way. So we can show that there is a coarse-grain such that we get close to 1 exponentially in the size of the coarse-grain. So by coarse-grain, we can exponentially get fast. We can exponentially get to the ideal intersubjectivity. And this function are basically function just of the initial temperature of the environments. So this is, we proved this analytically just for the dimension 2, but we have some numerical evidence also for larger dimension, which is a bit more complicated from the mathematical point of view. So this is just to show that this gamma function decreases exponentially as LCG with the same idea that we have used in the proof for the S equal to. As a final thing that I want to mention is, okay, we have this bound, but let's consider a natural model that is used in the emergence of objectivity framework and ask how close we get to this bound. So I consider a very basic model, which is sigma z interaction, and an initial state, which is this one, and we can use this model because it's efficiently described in terms of spin states, so we can basically increase a lot the dimension of the environments without having numerical issues. So here's what we find, is that by coarse, we also coarse-grain on this model, and we see that our bound, so here I'm plotting not the agreement, but the disagreement, which is basically 1 minus the agreement, and so we have, instead of an upper bound, a lower bound, which is the red line, and we see that there is a gap, of course. The fact that this can be understood by the fact that the optimal unitary of the theorem that I stated before, does not correspond to the sigma z interaction, so there are better unitaries in this regard. But still we get a sort of exponential decay, which is a bit delayed in terms of the size of the coarse grain. And something similar happened to the bias. Sure. So the real one is the red. So this is the disagreement. So this is the bound. Yes, and this is the one that is the minimum of the disagreement of respect to this unitary. So the bound is of course satisfied, but there is a gap between the bound and the disagreement. We can exclude this, as I said, because maybe the unitary, I mean, not maybe, but the unitary is not the optimal one. But still, we have an exponential decay in terms of the size of the coarse grain. It's just a bit delayed in terms of the usage. And something similar happens for the bias here. So we showed that as expected, the coarse grain is effective not only at the level of the bound, but also at the level of specific dynamics to obtain ideal intersubjectivity.
Is it obvious that the exponential behavior is at same?
Sorry?
Is it obvious that the exponential decay is at same after that size or something?
You mean the one for the model?
Yes.
What do you mean by obvious?
Like from here, I cannot tell that there's going to be an achievement. Like there's not. It's not super clear.
I think it's okay. The fact is, this one is an exponential decay because this is for dimension 2, so it's basically this one. Yes, it's basically this one, just this part, because it's 1 minus this part. So, okay, heuristically, I would say that basically this is going somehow with the same shape, with the same linear. So I would conclude that it's going exponential from this. I don't know if you agree. But, yeah. Okay. So a very last thing is also we look at a very last thing is here. I also wanted to plot agreement and bias in terms of like time dependence to show that something that we have not explored yet is the fact that the coarse grain. So the different line correspond to different coarse grains. So the blue is for like no coarse grain and orange coarse grain with subsystem and so on. And we wanted to show this plot because it's interesting because the coarse grain does not only affect the value, the maximum or the minimum value of the agreement and the bias, but also change the time at which we almost obtain one. So coarse grain somehow also affect the speed of measurement if we want. Something that we have not explored yet.
So it's the difference between the different colors?
The different color is the size of the coarse grain. So if okay, so the blue one is basically no coarse grain, and the orange one is when I group 2 subsystem, the green one 4, and so on. So
the color is the same.
The color is the same. Yes, it's yes.
We go for less coarse grain blue.
Yes. Yes. So the red one is more coarse grain. The orange I group together the more subsistence, and we see that of course with this coarse grain we approach 1 in the agreement, but we also at a certain point here we do not see too much. This is because of course here we basically reach to -6 to the -8. We do not see this from this plot, this difference in the peak here, but we see that we reach basically 1 faster. And this is what I wanted to show. Yes.
So you wanted the time here in 1 unit?
It's I put everything, these units. So this is why you see also the recurrence basically, because all the system interacts with the same strength, so there is a very quick recurrence. Okay, so conclusions. So as I showed you, I proved some theorem just for ideal intersubjectivity, and I also proved some bounds to non-ideal intersubjectivity, and we showed that everything depends on this function, which is just a property of the initial resource of the environment. And there are different methods to mitigate the gap between non-ideal and ideal intersubjectivity. One of these is cooling, the other one is coarse-graining. And the coarse-graining method proves to be efficient also in, yes, okay, this is what I just said, sorry. And we compared our result to this standard physical model for the emergence of objectivity. And most of relevant scenarios, such as SBS states or quantum Darwinism, must satisfy these bounds. Some perspectives, we would like to explore a bit the limitation on the unitary side, so how close we can get to ideal intersubjectivity if we consider thermal or Gibbs preserving operation instead of just an arbitrary unitary. And also, we would like to explore a bit how this coarse-grain affect the speed of measurement and if there is any fundamental bound after which we do not go faster, basically. And I would like to thank my collaborators, Felix Binders in Trinity College and Tiago de Barba from University of Technology of Paraná and the University of Technology of Wien. And the paper should be on archive soon, hopefully. So thank you. Thank you for that.
So I can ask you a relatively basic question. You went to the slide in relation to the intersubjectivity, objectivity, Darwinism.
Yes, maybe
so,
faster.
When you were there. So quantum objectivity is, you define it in terms of SBS states, which I understand is a way to quantify how many observers agree on the system, right?
Sorry, okay.
So quantum objectivity, for example, you mentioned SBS, SBS
yes.
factor, yes. So this kind of quantifies how many observers agree on the state of the system, right? And Darwinism is something kind of similar, not identical, but when you have the exploration in Darwinism. These are both features of a specific state.
Yes. Yes.
So, but other things like quantum decoherence is kind of intrinsically defined as a feature of the dynamic of state.
Yeah.
So how do you relate them directly one to the other? Right? How do you say one is like included or integration with the other?
Yeah, no, I mean, my idea was not to give like a precise statement to this diagram. It was basically to say that there is a sort of hierarchy between this framework, because basically quantum Darwinism is included in quantum decoherence in a way. Of course, as you said, the quantum decoherence and intersubjectivity are defined more on the dynamical level rather than just of the state. So they are a bit more general, and this I try to capture by considering the fact that there is also some part of intersubjectivity that's not perfectly included in quantum decoherence, and in the same way as the quantum decoherence is not perfectly included in quantum Darwinism. So it was just to give you more an idea of the relationship of the hierarchy, not to be understood as a precise statement, as a quantum.
And the coherence here you mean pointer states, right?
Yeah. Yeah.
And so another one here actually, so I didn't quite catch, so at an intuitive level, how do you understand the distinction between intersubjectivity and Darwinism / objectivity here?
You mean this one?
Yes.
So I've not understood this yet perfectly, but so of course, one thing for sure is that if the initial state is pure, which is not discussed, of course, it's not included in my discussion, but let's say that our initial state is pure, then the part that is not included in quantum decoherence is empty. Because if you have an initial pure state and you have intersubjectivity, so broadcasting, then the state of the system must decohere in the same basis.
When you say pure here, I mean specifically the system is
state and environment, overall.
Okay.
Yeah. And for instance, of course, in the quantum objectivity falls into intersubjectivity, but intersubjectivity includes also states that have quantum discord. So it's not perfectly included in the quantum objectivity or the SBS sort of.
So you have like a simple example of say that it's highly intersubjective, but it's not in everything else, like it's objective, etc.
I would say you can think of it's very it's not something like natural to think, but if you think like a system and multiple environments or qubits, and you first swap the system to an environment, and then you do CNOTs.
Okay.
Basically, you have transformed the initial state of the system to something arbitrary, which was in the initial state of the environment, and then by doing the CNOT, you copy the information to all the environments. So you get something that is intersubjective because you copied the information of the initial state of the system, but the initial state of the system now is something that is completely unrelated to the initial state of the system.
Can you understand that intersubjectivity means that the information of the initial information about the system is somewhere in the environment, but you're not asking about redundancy?
You do not ask. I would say that the subjectivity includes also some sort of destructive measurement in a way. So you are kind of not considering the state of the system anymore at the end of the process.
Yeah. And then, sorry, another question by the example you just said. So this example, for example, isn't it intrinsically dynamic on the system? Like if you think of a state that is initial, you have an initial state and you've got a bunch of swaps, and then now the information is hidden into the environment, etc. Which state am I considering to define intersubjectivity or whatever? You know, like if I have to go to quantum objectivity, with this example, I would have to choose the initial state and then define the state and define it from there. But it seems like for intersubjectivity, I have to consider the whole.
Yeah, the 2 points, sort of 2 points in time. You need some sort of distinction at that level. So
you need like a channel.
Yeah, if you wish, yes.
Okay.
Yeah, so it's true. The comparison here is a bit forced in the sense that I'm comparing the property of a state with property of a process or dynamics. But yeah, somehow it gives the idea that there is some relationship at this level. Anyhow, yeah.
Questions? With the third law, partial agreement.
Partial agreement.
So the effect of partial agreement defining some.
I think we asked this question ourselves. I don't think so, because what you can do, if your environments are all thermal or full rank, you can kind of, as a pre-measurement step, cool some of them with other environments, but still you will never get a pure state from that. So perfect agreement is not possible. You could improve agreement on subsystem if you do that, but that this will imply that you are worsening the agreement on another side. Yeah.
Anything else? If not, we thank Alessandro again. There is a question. Yeah,